We've got another example. This one, what we're going to do is we are going to find volume. Units need to be cubic meters. That is occupied by 2 kilograms of water at a pressure of 100 bar and a temperature of 400 degrees Celsius. And we're going to do this using two methods. We're going to use this compressibility chart that we just talked about, and we're going to use the old-fashioned steam tables. Then we're going to compare our results. Now, to use the compressibility chart, let's start with this. We need to get the reduced temperature and the reduced pressure. Let's find those. So reduced pressure is going to be P over PC. For water, you look up the value for the critical pressure in the table. You get 220.9 bar. Current pressure is 100 bar. Notice those units cancel. So we get 0.45 for our reduced pressure. For the reduced temperature, remember that is T over TC. We'll look up that critical temperature in the table for water, and we get 374 degrees Celsius. Our current temperature is 400 degrees Celsius. Those units cancel. This ends up being 1.07. Now, our pressure is low, it's 0.45. We're going to use that figure A1 to figure out what Z should be. And if we look at A1, that's what it looks like. This is the table where our reduced pressure can go from 0 to 1. Our reduced pressure is 0.45 and TR is 1.07. We are going to approximate TR to be 1.05 because 1.05 is right here, so we have that data point. It's the closest thing we'll get. Now let's find 0.45. So that's going to be this line right here. Now we just need to match it up with the 1.05. So 1.05 is a solid line, and it's going to intersect right there, approximately. Okay, right here, and then we just go over to the left. So this line right here would be 0.85. We're a little bit above that. So I'm going to say that Z is approximately 0.86. On these problems, you're going to have to kind of guess, make your best guess on what you think Z is, because it's obviously not going to be too accurate. And that was from the figure. Now we've got Z. We're looking for volume. So we don't have volume yet, we just have this Z number. We need to figure out what to do with that. Remember that Z is equal to PV over RT. Now, if we can find this specific volume, then using the mass, we will be able to find volume. All right, so let's do that next. And I'm going to come down here on this next line and finish this because we're going to have some unit conversions. So this isn't enough room. We're going to have 0.86. That's going to be equal to our pressure, which is 100 bar. And before I finish the top, let's go down here in the denominator. We're going to have R times T. The R value we need for water is going to be 0.4614. Those units are kilojoules per kilogram Kelvin. Our temperature, we are at 400 degrees Celsius. Now, am I just going to plug in 400 degrees Celsius here? No, we're not going to do that, because remember, our equations need absolute temperature scales. So Celsius is not an absolute temperature scale, so we need to take that 400 and we are going to add 273.15, and then that will get us to kelvins. Now, if we look at our units here, the kelvins go away, that's good, but now we have bar up here, we got kilojoules per kilogram right here. Now, we're still going to have specific volume up here also. But we need to get rid of this bar term. So let's do our conversions. We're going to have 10 to the 5th Newton per square meter per bar times 1 kilojoule per 10 cubed Newton meters. So this will convert bar over to kilojoules, and then multiplied by that specific volume. Now if you do the math here, you'll get 267.11 equals 10,000 V. So from this you can find your specific volume, which is 0.0267. That's cubic meters per kilogram. Now we don't want specific volume, we want regular volume. We're going to take this number, notice it's got kilograms here in the denominator of the units. All we need to do is multiply by mass to get volume. So volume is going to be 2 kilograms, because that's our mass, times 0.0267 cubic meters per kilogram. Kilograms cancel. Now we're left with units of volume. Our volume then is 0.0534 cubic meters. So this is the volume that we found using the compressibility chart. Now that we've got that done, we want to use the steam table and find volume. And then we're going to compare the result. This will be part B. So remember, we've got a pressure of 100 bar, temperature is 400 degrees Celsius. Now we've got our pressure temperature combination. We can use the table to figure out what specific volume we have. So again, you're going to have to figure out what you have. Do you have compressed liquid? Do you have liquid vapor mixture? Do you have superheated vapor? You're going to have to figure that out. Let's draw our vapor dome here to figure out what we've got. Now, let's start with this pressure. We've got a pressure of 100 bar. Let's look in the liquid vapor table and figure out what the saturation temperature is. If you go to table A3, which is the pressure table, if we come to this pressure table, find 100, here it is down here at the bottom, we have a saturation temperature of 311.1. Now that we know that, we can put that right here. Remember, that's temperature, that's V. And this was for 100 bar. Our temperature is at 400. Now obviously that's higher than 311, so let's put 400 here. We need to find where that temperature intersects our pressure. So we're going to be over here. That is what? Superheated vapor, that's right. We need to use the superheated vapor table to get our specific volume. That is table A4. Now notice how we keep having to figure out what table we're in. That's why I kept doing a bunch of examples on how to choose the table, because it just keeps popping up. Now that we have this table, we know what table to go to. You're just going to look up your conditions, and then you will be able to find V. The V number you'll get is 0.02461. That is cubic meters per kilogram. To get volume, you just take this number, multiply by mass. We're going to have 2 kilograms times 0.02461 cubic meters per kilogram. Cancel those units. That gives you a volume of 0.05282 cubic meters. Right. So that's your volume you get using the steam tables. Now obviously this is going to be a little more accurate than this one, because here we kind of had to guess at what Z was. We did some approximating. All right, so this is going to have less error in it. Now if we compare the results, let's just put this over this. We get 0.05282 over 0.0534. That equals 0.989. So the difference is 1 minus 0.989, which is basically 1.1%. So there's a 1.1% difference that we get. And a lot of that is brought about by the fact that we kind of had to guesstimate our values. Now, this Z that we had was 0.86. All right, so that is not close enough to consider this as being an ideal gas. All right, so if we were to actually consider this as being an ideal gas and say Z is 1, so let's just say we wanted to be lazy and not find the reduced pressure and the reduced temperature, and we just wanted to assume that it was 1. Let's see what we get. So if you were to assume that, then you'd get a specific volume of 0.3106. And that would give you a volume of twice this number, so 2 times specific volume, which would give you 0.0621. Now, if you do the same comparison, if you put the 0.0621 number over 0.05282, you're going to get 1.176. Notice the big difference here. So this is essentially saying that we are off by 17.6%. Okay, so you don't want to assume you have an ideal gas unless you actually can make that assumption, because otherwise you're going to have a lot of error put into your calculations. You don't want to have a 17.6% difference compared to what the actual value is. So that's just a note here that if you're really unsure if you can use ideal gas or not, you can always calculate your reduced temperature and reduced pressure, find Z, and Z should be equal to 1, or very, very, very close to 1. 0.86 is not close enough. All right, that's the end of that one. We'll save the next example for the next video. See you soon.